Okay everyone, welcome back to the C++ series. This is going to be episode 3, and today we're going to be talking about arithmetic types, more specifically the floating point side of things. Last time we talked about integral types, if you remember, so we talked about integers, so whole numbers without a fractional piece, and then we also included the Boolean and character types under that integral group of arithmetic types. Now before I get started, I do want to throw out a quick reminder again to beginners to watch those before you watch videos and articles down in the description below. Again, those are great because if there's something I talk about, some terminology I use that I don't really go into detail about, you'll have a general overview of what we're discussing. And I try not to make those videos and articles very long. I mean, you shouldn't be spending any more than 2 or 3 minutes on each one max. The point of those aren't to make you an absolute master in whatever the topic is. It's just to give you a general understanding, so when I bring it up in the video, you aren't completely lost and it doesn't sound like jargon. So let's jump into things here. If you remember last time we talked about integral types, so we covered shorts, ints, longs, chars, and bools. Today we're going to be talking about the floating point types, and I'm going to try to make this video a little shorter because there's only 3 that we have to cover. Floats, doubles, and long doubles. So again, floating point types represent decimal or any numbers with like a fraction or a decimal. It's technically decimal because there isn't a baked-in type with a fraction, and you'll see that later on how we can actually build our own type that's a fraction. But in the baked-in C++ floating point types, these are just decimal types basically. So any numbers that have a decimal. And just like the integer types, you can see that the floating point types, there's multiple floating point types. So again, we have float, we have double, and then we also have a long double. So if we jump into our editor here, we can go ahead and right below our long from last time, we can create a variable name or a variable of type float. And we'll just say var float. And we're going to set this equal to with the assignment operator. Remember our assignment operator from last time. This is how we assign a value to something. We're going to assign that equal to a decimal number. We're going to do something really simple to start. We'll just say something like 1.2. So we have assigned this float variable to the value 1.2, or I guess a more proper way to say it is that we've actually assigned 1.2 to this float variable. Now likewise, we can go ahead and create a double. We'll just call that var double, and we'll set that equal to 1.23. And then we can also create we have to create a long double, and we'll say var long double equals 1.234, just to differentiate all of them. So you'll often hear floating point types, or not floating point types, but I should say float data type specifically, referred to as single precision. Now all this means, and again, when we get to the video on binary, I'll be talking about this again, but all that single precision means is that it is made up or consists of one word in a computer, and a word in a computer is just 32 bits. You'll hear double data types referred to as double precision, and that just means it's made up of 2 words in a computer, and the 2 words in a computer just means it is 64 bits. I know when you think of words, you think of letters and words you would read out of a book or something, but to a computer, one single word is a segment of memory, a segment of storage almost of 32 bits. And so likewise then, if we doubled it to have 2 words, we have 64 bits. So I'll go ahead and write in here too, 1 word, 2 words. Now long doubles you often hear referred to as extended precision. And extended precision usually just means that it is either, it's basically something that's more than the 2 standard precision types in a computer, which is 32 bits, 1 word, 64 bits, just 2 words. So oftentimes you'll see this probably as either 96 bits or we'll say 128 bits, which would be 3 or 4 words. That being because 32 bits would be 1 word, so 3 times that would be 96, 4 times that would be 128. Now the size of data types in terms of bits and words will be a lot more important when we get to the video on binary. So I wanted to get that out there because this is part of the floating point type concept, and just is kind of to plant the seed for that video. But what I want to talk about more that's more important in this video is actually the number of significant digits that each floating point type can hold. And so I'm going to go ahead and get rid of these the comments here real quick. So for float data types, the C++ standard actually specifies that the minimum number of significant figures for a floating type is 6 sig figs, so 6 significant figures or 6 significant digits. Now this is a minimum that the C++ standard specifies, so different compilers, different systems in general can obviously specify a different minimum. I think normally most of the time floats can support right around like 7 sig figs, and likewise doubles can support, or I should say the C++ standard specifies a minimum of 10 sig figs, and most of the time you'll see doubles support more like 16 significant digits or 16 significant figures. Now long doubles also have a 10 sig fig minimum for the, or I should say specified by the C++ standard. Now long doubles are mostly used to accommodate special floating point hardware that do like these crazy calculations, so you don't see these used as often in typical C++ applications. And because they're used for such specific use case scenarios, you see these change more often from compiler to compiler, from system to system. And so we won't be using this very much in this series just because it takes up a lot more space to begin with. I mean, you're talking double, in some cases, the amount of space as a double variable. And the computation time is a lot longer too for unnecessary precision that we won't be needing. So, but I did want to bring it up because it is part of the floating point type family in the arithmetic type category. So now if you don't remember what floating point numbers are, I've linked a Khan Academy video down below in the before you watch section. Khan does a great job of giving a quick refresher on what sig figs are and what they're meant for, but just as a quick recap, and I won't be able to explain this as well as him, but basically significant figures are just help identify and represent which digits in a number are important in representing the precision of a particular number. So if we had a number 0.00100, these 3 numbers would be the sig figs for this whole number, and that being because we could easily get rid of these 2 zeros and this would be the same number still, but obviously if we included these numbers, it was for a reason. It was because we wanted the precision to go down to this many decimal places, because if we had to convert units of measurement or something, then these would be important. And likewise, if we had a number that was like, and I think this was close to one of the examples he uses in the video, but if we had a number like 14,000 .01, well then this would have 1, 2, 3, 4, 5, 6, 7 sig figs, because all of these numbers are important in calculating the precision of this number. Now, finally, let me see if I can find some more space here. If we didn't have this decimal point, and all we had was this 14,000, if there's no decimal point specified at the end here, then the only 2 sig figs that we would basically count here would be these first 2, because there's a little bit of ambiguity here, as I'll mention in the video, and that being because if we just see the number 14,000, it's very possible that whoever calculated this number for some reason was only calculating to the nearest thousand, and maybe they're lucky, maybe they were calculating to the nearest ones place, and they just happened to get 14,000. But odds are that we would just assume that they're only rounding to the nearest thousands here, or tens of thousands, or whatever it might be. So here we would just say there's only 2 Sig Figs. Now I probably completely slaughtered that, so if that didn't make sense, I'm serious. Please go watch that Khan Academy video. It will make a lot more sense. So one of the only other things that I want to talk about is what happens when you overflow one of these floating point data types with too many sig figs, more than it can support. So I'm going to add something into our little program here real quick. And don't worry, because you're not going to know what this means more than likely if you're a beginner. Basically, by default, C++, or at least the compiler we're using, only allows 6 significant digits to be printed out to the console window. So all this is doing is allowing us to use this in our little print statement here. And it's just saying that now we're setting the default to 16 significant digits that we can print out instead of 6. Just so we can demonstrate what we're talking about with some of these floating point types. And so to start, I'm actually going to take this, I'm going to copy this, and I'm going to just do one of the regular print statements that we've been doing here with var float. I'm going to comment this out for a minute. So if we run this right now, we print our var float to the console, we'll expect to see 1.2. And we do. Now, if we increase this decimal point precision to 3456, put this out, we should still expect to see this entire number printed out to the console because this is 6 significant digits, and we know that via the C++ standard, float types have to be a minimum of 6 sig figs. And there we go, we get the whole number. So now if we increase this to some crazy astronomical random floating point number that we know a float won't be able to support, and I'm going to comment out this one now, and I'm going to go back to our print statement that will support at least 16 sig figs. If we print this out now, let's see what we get. And so you'll see here that it's accurate up to a certain point. So we have 1.23, and here we have 1.23. Then we have 4, 5, 6. Here we have 4, 5, 6. And then you see the next digit we have is a 4. And here we have a 4. But then notice after that, these two numbers are entirely different. So this basically tells us here that our compiler is supporting 1, 2, 3, 4, 5, 6, 7 sig figs for floating point types. Because after that, the number just goes haywire. And the reason being is because if you overflow a floating point type with too many significant figures, the default behavior specified by the C++ standard is being undefined. And in general, what undefined means is that you have no control over what's going to happen. It's the machine, the compiler will do something, but we don't know specifically what it's going to do. And that's why you're seeing this jargon of a number here. So you always have to keep in mind how many significant figures C++ is supporting, and because of that, most often what you want to do is use doubles when you're doing floating point computations. And that just mainly because doubles will most often support the correct amount of significant figures for a calculation. And then you also won't have to worry about overflowing your float variable if you go over the maximum amount of precision that a float can support. So what I'm actually going to do now is I'm going to copy this decimal part from our float variable, or I should say the value in our float variable, and I'm going to paste that into the decimal portion of our double variable. And so I'm also going to replace our float variable name with the double variable name, and I'm going to increase our precision that the compiler will let us print to the console to 20. And so now that we have our double in our print statement, let's go ahead and run this. And let's sort of compare and contrast these again. Let's observe and see what the results are here. So now we have for our double value that got printed out, we have 1.234, 1.234, then we have 56423, we have 56423, Then we have 4, 5, 2, 4. Here we have 4, 5, 2, 4. And then we have 5, 2, 4. And then here we have 5, 2, 4. You'll notice after that we have 2, 3, 9, 9. And here we have 2, 5, 2, 3, 3, 4, 5, 2. Something totally different. And so what does that tell us? First off, it tells us that it has the same sort of undefined behavior that a float variable would have if we overflow the maximum amount of precision, which is the compiler. Well, we actually don't know what that behavior would be. That's why we're seeing this jargon number here, the jargon ending to the number, because the behavior is undefined. So we don't know what the machine or what our system is going to do. In that case, it's not defined. And we can also see then that doubles, at least on this compiler, the Visual C++ compiler supports 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 significant digits. And so that's about it, guys. I'm going to wrap this episode up here. That's basically it for at least the basics of floating point types. What we're going to do next time is I was going to go over type conversions and unsigned and signed types next, but I kind of decided on the fly that I want to actually do a very short episode on doing some mathematical calculations with some of the integral types and the floating point types. That way we're not just seeing simple assignment statements here, and like we did in the in the integral video, but we can actually do some addition, some subtraction, some multiplication and stuff like that. Now, I'm going to have an entirely separate episode on all the different mathematical operators. I'm just going to use them in the next episode just to demonstrate some of the things you can do with basically any of like the number kind of data types. We're also going to see that you can actually use, although it's not recommended per se, you can use the char data type and the Boolean data type in mathematical operations like subtraction, addition, and all that, and then we're going to see why. And what's really going to wrap all of this stuff together about data types is the video on binary that I'm going to be making as soon as we get through a lot of these basic concepts about data types. So stay tuned for that. And with that, I am going to wrap the video up there, and so I will see you next time.